Good evening, everyone. Welcome to our plenary panel on the future of subduction zone science. My name is Anne Sheehan, and I'm a geophysics professor at the University of Colorado Boulder, and I will be serving as the moderator for this panel. The format is that each of our panelists is going to give a short overview of kind of their thoughts and some of what they think are some of the big outstanding questions in subduction zone science. And this plenary or panel is kind of a conversation to just talk about some of these issues and other questions. And I have some questions to kind of help prime the pump for the discussion. And also David Schmidt will be monitoring your questions, and we can interject those as we go. And we will also have time at the end for questions from the audience. And yeah, I'd definitely like to thank Jackie and David for organizing this panel and for assembling this talented panel of subduction zone scientists, each of whom focus on a different part of the subduction zone system. And let me go ahead and start by introducing our distinguished panel. So why don't I'll start on the right with Dr. Shawn Wei. Dr. Shawn Wei is an endowed assistant professor of geological sciences in the Department of Earth and Environmental Sciences at Michigan State University. He is a seismologist with broad interests in Earth's mantle structure, particularly those associated with subduction zones. His recent work has been focused on imaging seismic structures of the Tonga-Lau subduction system, intermediate depth seismicity in Tonga and Alaska, and also looking at the mantle transition zone. One of his major interests in terms of methodology is seismic attenuation. Shawn uses a variety of seismic and geophysical techniques to study mantle discontinuities, subduction zones, and melt and volatiles in the mantle. He has field experience in the South Pacific, the US Midwest, China, and Antarctica, and he also works with global data sets. Shawn was recently awarded an NSF Career Award, and he's also PI in an upcoming ocean bottom seismic experiment for the Tonga-Samoa region. And then in the center is Dr. John Power. He's a research geophysicist at the USGS Alaska Volcano Observatory, or AVO, in Anchorage, Alaska. He's a specialist in volcano seismicity and volcano forecasting. He's been with AVO for over 30 years and played a central role in expanding their seismic network throughout the Aleutian arc from just 4 volcanoes in the 1990s to over 34 volcanoes today. He's been active in eruption forecasting efforts at many Alaska volcanoes, particularly in the Cook Inlet, Augustine Volcano, Redoubt Volcano, and then internationally at Montserrat and Mount Pinatubo. And yeah, I was excited to learn that he was part of the Mount Pinatubo response team. I often show my intro geology class. There's a NOVA special called In the Path of a Killer Volcano, which I think is awesome. You should check it out. And he's in that. And their eruption warnings saved thousands of lives. There was, huge evacuation there. And I think I already talked about his research interests, and he's also done a lot of work on deep, long-period earthquakes as potential indicators of magmatic recharge. So at this point, I'm going to turn it over to the panelists. Each one is going to come up here and show a few slides. Laura, yes. Oh, I didn't introduce, oh my gosh. Laura needs no introduction. Okay, yeah, I have one job. Sorry.
That's okay.
Okay, Laura. Dr. Laura Wallace is a senior research scientist at the University of Texas Institute for Geophysics and is a principal scientist at GNS Science in New Zealand. Laura uses geodetic methods to investigate plate boundary crustal deformation throughout the earthquake cycle. She is particularly interested in understanding the physical mechanisms that controls subduction earthquakes and slow slip events, and she has worked on these issues throughout New Zealand and the Western Pacific. Laura has led several major initiatives to reveal the physical processes that control slip behavior on subduction zones, including scientific ocean drilling and numerous seafloor geodetic and ocean bottom seismic experiments at the Hikurangi subduction zone. Laura is a fellow of the Royal Society of New Zealand and has been awarded the Mackay Hammer Award from the GNS Society of New Zealand, and is also a 4-time winner or co-winner of the New Zealand Geophysics Prize. And with that, I think now Laura gets to show a few slides. So yeah, thank you for paying attention there. Yeah, you get
Get this mask off. Let's see. So I guess I represent what you would call the shallow part of the system, since my interests are more out kind of in the fork and the subduction megathrust. So I'm going to talk about some of the questions that keep me up at night, and I know keep a lot of the rest of you up at night too, to kick off some of this discussion. And I guess one of the big ones for me, and I know we've been asking these questions for many years, but it's pretty clear from geodetic observations and seismological observations that subduction zones slip in a really broad spectrum of ways. Some of them lock up and accumulate stress for hundreds of years and then slip in big earthquakes, while some of these other subduction zones tend to creep either steadily or in episodic slow slip events. And so a big question is what causes this real diversity of slip behavior that we observe at subduction zones worldwide? What are some of the physical mechanisms causing this? And also, are these slip behaviors in a given location actually persistent in time over multiple seismic cycles? Or do we actually see big variations in slip behavior in a given location over many seismic cycles? And can whoever's controlling this clock up here actually start it? Because it's still on 60 minutes and I could go on way too long, probably. And so there's, obviously a lot of ideas people have been putting forward for what causes these different types of slip behaviors that we observe at subduction zones, and involving things like fluid pressure and frictional properties, different scales of heterogeneity within the fault zone, thermal controls, and also the properties of the crust surrounding the faults have all been proposed as potential controls. I think probably varying degrees of all of these types of things are going on to control the things that we observe in terms of subduction slip behavior. But a big question is, how do these things feed back on each other and interact? And also, can there be a single unifying explanation to explain everything that we see? I'm skeptical that there is a single explanation, because subduction zones are such diverse beasts, but I think it's still worth pursuing that. One of the other issues, is really thinking, I think we need to think hard about, we've learned a lot in the last few decades about the processes controlling subduction earthquakes and slow slip events, although we haven't fully narrowed in on the kind of final answers. But how do we actually bring this into informing seismic hazard? And that's where the real societal implications come in here. And particularly for subduction zones where we don't have long instrumental records, or we don't have long high-quality paleoseismic records to inform us about past subduction earthquake occurrence, are there specific characteristics of subduction zones that may make them more or less likely to produce great earthquakes? And then I think we need to do a better job bringing in a lot of the observational constraints that have been made at many subduction zones over the years, particularly on the physical properties and the processes, and bring those together to underpin some of these physics-based earthquake cycle simulations these models that people have been developing, in particular to generate synthetic seismicity catalogs that can be used in probabilistic seismic hazard assessment and tsunami hazard assessment. But really, another thing I think we need to think about before taking that leap into really using those in a major way is really testing and vetting those simulator outputs. The physics might not be right in those models. And we really need much more precise, much longer paleoseismic records to verify those and validate those simulations, and also better instrumental records as well. And then another final thing in terms of the hazards issues, that this really came up to the fore with the magnitude 9 earthquake in northern Japan in 2011. Oh my God, have I really been going on that long? Or is they started it, okay. There was really good evidence for foreshocks and a slow slip event preceding the magnitude 9 event, which may have actually triggered that event. And this raises the questions, can we reliably identify precursors to great subduction earthquakes that could then be used and potentially in an early warning sense, or at least to improve our operational earthquake forecasts. This is something I had firsthand experience with in New Zealand when we had, following the Kaikoura earthquake, almost all of our slow slip areas on the Hikurangi subduction zone started slipping all at once, and they were surrounding this big locked patch, and we were very worried at the time, are we going to have a magnitude 8 earthquake sometime in the next month or two? And we had to address this and bring this into our forecasts, but the problem was, and I think this is still a problem, we don't have great ways of doing that yet. So I think these are things that we need to be striving for in the future. So in terms of wrapping up, what sorts of experiments and data are needed to get at some of these big questions? I think the big frontier, and I know a lot of people in the room feel the same way, is the big frontier is beneath the ocean. That's where our biggest observational gap is. That's where potentially the most dangerous portions of subduction megathrusts are. It's where a lot of the earthquakes are going to be generated, and the tsunami-generating earthquakes are going to be happening there. So we really need to be advancing seafloor geodetic techniques, ocean bottom, more widespread use of ocean bottom seismology, and really start to get some long time series at some of these subduction zones, possibly via cabled networks. And then in terms of getting at what are the fundamental processes at play here, we also need a lot of multidisciplinary observations. And that kind of thing has already been done at a few subduction zones around the world, but I think it needs to be done much more widely, and including active and passive seismic imaging, scientific ocean drilling, and also things like magnetotellurics and controlled source EM. So that's all I have to say. So I'll hand it off to John to talk about volcanoes.
Thanks, Laura. And I want to start by thanking everyone for coming so late in the day, and also the meeting organizers for putting this together. And a special thanks to the number of individuals that I have pestered with questions for this presentation over the past couple weeks. I won't mention your names, but you know who you are. Oops. Where are we here?
So left goes forward and right goes backwards.
Going the wrong way.
Oh, maybe I'm wrong.
Here we go. No, my role tonight is to ask questions or pose questions or speculations about magmatic systems and inconvergent margins, and how we might approach some of these questions going forward. The way that I've started here is with a cartoon that Shawn has put together and loaned to me. And these are the bigger picture questions that I could think of. How things like convergence rate, plate coupling, obliquity, moment release, composition of subductive material, tectonic tremor can be linked to magma generation, transport, and eruption in convergent margins. These are all areas that I think people have looked at to one degree or another in the past, although I think that, and while some of them remain very active areas of research, some of them have languished more. We also have, I think, developing in recent years additional observations and improved instrumental records that actually are going to allow us to address some of these questions in a more fundamental way. The other thing that I think begins to play into some of these questions that have been, some of which have been around for quite a while, is the time scale that these are occurring over. And oftentimes, particularly with magmatic systems, we are looking at processes that are occurring on decadal or multi-decadal or even hundreds to thousands of years. And I think as we move forward with our instrumental records, we'll be able to address some of these questions in a much more meaningful way. The next question that I wanted to pose was how magma may traverse this overlying plate, and which I think is critical for many of our investigations and our understandings of magmatic systems. What I've shown in this diagram here, if I can make this work, this is the Aleutian Arc, and the black triangles are the position of Holocene eruptive centers. I've put on here large red circles that show the positions of calderas, and by calderas I mean things that have an area greater than 5 square kilometers. This precludes the little tiny craters that exist at the top of many volcanoes. These are scaled not to the map scale, but to the scale you see here on the upper part of the diagram. Along the bottom of the arc, I've put vectors that show the convergence rate and direction. And the thing that is of, I think, critical importance, or one of the critical research questions, is where within volcanic arcs we're forming these large, shallow accumulations of magma that can form large caldera-forming eruptions, as opposed to portions of arcs where we may see, repeated smaller eruptions where we don't form these larger magmatic systems at shallow depth. A number of researchers have discussed this in the past, particularly Hughes and Mahood in 2011. One of their conclusions looking at arcs worldwide was that in places where we had orthogonal subduction at high rates, greater than 7 centimeters per year, we were likely to form these large caldera-forming eruptions and large shallow accumulations of magma. What I've shown here is, this is a photograph of Okmok caldera in the central Aleutians. This volcano experienced a very large caldera-forming eruption in about 43 BCE, which has recently been linked by McConnell and others to the fall of the Roman Republic. These kinds of eruptions, we really haven't seen on the planet since probably the early 1800s with Tambora. These lead to things like pandemics, crop failures, widespread global hazards, short-term climate change. It's, I think, critical that we move forward with trying to understand how these accumulations occur and what destabilizes these large magma accumulations, forming these very large eruptions. For my last slide, I'm going to focus more on